Because of the limitations outlined in the previous session, the array implementation cannot be used for large-scale applications where queues are implemented. Alternative to the array implementation is linked list implementation of queue. The linked representation of queue with n elements has storage requirement of big O of n, while the time requirement for operation is big O of 1 in a linked queue. Each node consists of two parts, a data part and a link part. Each element of the queue points to its immediate next element in the memory. There are two pointers, the front pointer and the rear pointer maintained in the memory in the linked queue. The address of the queue's first element is contained in the front pointer, while the address of the queue's last element is contained in the rear pointer. At the front end and the back end, respectively, insertion and deletion are made. The queue is empty if both front and rear are null. There are two fundamental operations performed on the linked queues. They are insertion and deletion. First, we will discuss about the insertion operation. By appending an element to the end of the queue, the insert operation appends the queue. The final element in the queue will be the new one. We will use this line to allocate memory for the new node pointer. Inserting this new node pointer into the connected queue can go in one of the two ways. The first case involves adding an element to the queue that is empty. Under these circumstances, front is equal to null becomes true. At this time, the front and the rear pointers' next points will both point to null, making the new element the only one in the queue. Here, this line assigns the value of the item to the data member of the structure that pointer is pointing to. This part of the code is conditional statement. It checks if the front pointer is null. If it is, it means the queue is empty. If the queue is empty, front is null. Front and rear are assigned to pointer, which is the new node being added to the queue. Then front next and rear next are set to null, indicating that there is no other element in the queue. So in summary, if the queue is empty, pointer becomes the only node in the queue, and both front and rear point to it. In second scenario, there are multiple elements in the queue. It becomes false when the condition front is equal to null. To make the next pointer of the rear point to the new node pointer in this circumstance, we must update the end pointer rear. We also need to set the rear pointer to point to the newly inserted node pointer because this is a linked queue. Additionally, we must set the subsequent rear point to pointer to the null. This line sets the next pointer of the current rear node to point to the new node pointer that has been added to the queue. This line updates the rear pointer to point to the new node pointer, making the pointer the new rear of the queue. And this line ensures that the next pointer of the new rear node pointer is null, indicating the end of the queue. So in summary, this connects the current rear node to the new node pointer, and this updates the rear to point to the new node pointer. This sets the next pointer of the new rear node pointer to null, indicating the end of the queue. Now we will write an algorithm for insertion operation on linked queue. This allocates memory for a new node and assigns it to a pointer. This sets the data part of the new node to the value. This checks if the list is empty. If the list is not empty, front and rear are set to point to the new node pointer. This means that front and rear both point to the first node in the list. This sets the next pointer of the both front and rear to null as there is only one node in the list. Else, if the list is not empty, it sets the next pointer of the current last node that is rear to point to the new node, effectively linking the new node to the end of the list. This moves the rear pointer to the new last node pointer, and this sets the next pointer of the last new node that is rear to null, indicating the end of the list. Now let us write a C function to insert an element in a linked queue. This line allocates a memory for a new node and assigns the address of the allocated memory to a pointer. This checks if memory allocation was successful. If not, it prints overflow and returns, indicating that the function was unable to insert the new node. Else, this assigns the value of the item to the data member of the newly created node. This checks if the list is empty. If the list is empty, the front and rear are set to the newly created node pointer. Also, the front and next are set to null. Else, if the list is not empty, the new node is added after rear. Rear is updated to the point to the new node pointer and rear is updated to point to the new node. Now we will see the deletion operation performed on the linked queue. The element that is initially placed out of all the queue elements is removed during the deletion operation. First, we must determine whether or not the list is empty. If the list is empty, the condition front is equal to null becomes true. In this scenario, we just print the underflow to console and quit. Else it will delete the element that is pointed by the pointer front. For this reason, copy the node pointed by the front pointer into the pointer PTR. Now move the front pointer point to its next node and free the node pointed by the node PTR. These statements are utilized to do this. Here PTR is a pointer that will be used to temporarily store the address of the node that is being removed. This line moves the front pointer to the next node, effectively removing the first node from the linked list. Finally, this line deallocates the memory occupied by the node that was removed. In summary, this code segment removes the first node from the linked list and deallocates the memory occupied by that node. Let's see an algorithm for the same. First, we check if the front pointer is null. If it is null, it means the queue is empty. In this case, we print an error message and exit the function. After checking if the queue is empty, now we will create a temporary pointer and point it to the front of the queue. We create a temporary pointer temp and set it to point to the same node as front. Move the front pointer to the next node. We move the front pointer to the next node in the queue, effectively removing the first node from the queue. Next, we will free the memory occupied by the node printed by the temp. We use the function free to deallocate the memory occupied by the node pointed by the temp, which is the node we are removing from the queue. After deleting the node, we check if the queue is now empty. If the front pointer is null, it means the queue is empty. In this case, we set both front and rear pointers to null. Now let us write a C function for the same. First, we will check if the queue is empty as we already saw in the algorithm. The function first checks the queue is empty. This is done by checking if the front pointer is null. If it is null, it means the queue is empty and the function prints underflow and returns. Now we'll delete the first node. If the queue is not empty, it proceeds to delete the first node and this assigns the front pointer to the PTR pointer. This step is not necessary because PTR is a local variable and changing it won't affect the caller's front pointer. And this will move the front pointer to the next node. It moves the front pointer to the next node in the queue, effectively removing the first node from the queue. And this will free the memory occupied by the node. It deallocates the memory occupied by the node pointed by the PTR using the function free.